I want to talk about the distribution of moisture content in the unsaturated zone under both hydrostatic and non-hydrostatic conditions. So there's a few things you first need to be really on top of. The first is that to define head in the unsaturated zone, we use this equation here, that the head is defined as the elevation above some datum plus psi, where psi is the metric, this is the metric potential. It's really important to keep these words straight. Alternatively, we can define instead of the metric potential, we can take the absolute value of it, because remember, the metric potential psi is always less than zero in the soil zone or the unsaturated zone. So since we often don't like to work with negative numbers, sometimes we take the absolute value of it. We call that the metric suction. Small difference in word, big difference, because one is positive and one is negative here. And given that the metric suction is essentially the negative of the metric potential, we can also alternatively write that the head in the unsaturated zone is equal to Z minus the metric suction. So let's see what we're talking about here. So here we have on the left here, this gray area represents a cross section of the earth, and the gray area is the soil zone or the unsaturated zone. This little upside down triangle down here, that's the water table. So the water table is located 3 meters beneath the surface. And what we want to do is know what the moisture content is in the unsaturated zone. First, under the conditions of hydrostasis or hydrostatic conditions. What does that mean? That means the conditions that the water is not moving. And what determines whether the water moves or not? Darcy's law. Darcy's law can be written as that the velocity of water flow is equal to this hydraulic conductivity, a property of the medium, divided by the porosity, a property of the medium, times the change in head divided by a change in distance. So the basic idea is, as with all diffusion equations, if there is no flow, if the velocity is zero, that happens when the change in head is equal to zero. So if the head doesn't change, if there is no change in head that is other than zero, then we have no flow. So the condition of hydrostasis or hydrostatic equilibrium occurs when there is no change in head, or another way of saying that is everywhere within this gray area, the head has to be constant. It's the same value everywhere, and if it's the same value everywhere, then there's never a drive for water flow according to Darcy's law. So we have to focus in on, well, what is the head everywhere? And the easiest way to do that, remember when we define the head, it involves Z, and Z is the elevation above some datum elevation. So we can arbitrarily pick that datum elevation, and to make things really easy, I'm going to pick the datum elevation as the elevation of the water table. So this line here, this is the datum elevation. And at the water table, so the datum is the water table. So let's see if we can figure out what the head is at the water table. So the head at the water table will equal the elevation at the water table plus psi at the water table, or minus the matrix suction at the water table. Well, if the datum is the water table, then Z at the water table is just simply zero. And since psi, you might remember, psi can always be expressed as the pressure, the water pressure, divided by rho g, by definition, the water pressure at the water table is zero, so this is zero. And so psi at the water table is equal to zero. This is equal to zero too. So the head at the water table is identically zero. So that makes it really easy. If the head at the water table is zero, and the head within the entire gray zone here, the unsaturated or soil zone, is always the same, then the head everywhere here, using datum as the water table, head has to be a constant of zero. The head here is everywhere zero. So if I were to plot on the same vertical axis, this is a vertical axis, right? Now this Z represents here, just to be clear, elevation here represents, this is elevation Z above the water table. So this is increasing, right? So the surface is 3 meters above the water table is 0 meters above the water table. So if I plot Z versus head, what we just said is the head is everywhere the same and zero. So this is a really simple and boring graph. Just the head is everywhere the same, equal to a value of zero. Now think about what that means. Let's say we are at an elevation 1 meter above the water table. So let's actually use this equation over here, because I think this one makes it a little easier. This one over here in terms of matrix suction. So if the head is everywhere 0, let's say that z is equal to 1 meter, okay? 1 meter above the water table. Well then, if the head is 0, then the value of the suction has to also be 1 meter. In fact, whatever z is, right? Whatever z is, the suction, absolute value of psi, has to be exactly the same. If we're 2 meters above the water table, then psi has to be equal to 2 meters, right? So that the difference is always 0. So in other words, when we have hydrostatic conditions and H is equal to 0 here, we have the special condition that Z is equal to the matrix suction. So now let's think about what we want to know now. What we want to know originally was we want to know the moisture content in this soil zone. Do we have a relationship between Z and moisture? That's what we want. We want a relationship between Z, which is the elevation above the water table in our unsaturated zone, and the moisture content. Well, that's kind of hard to get at, but we have something really, really close. We have a relationship between psi and the moisture content. And since psi is equal to Z, that's the same thing. That's exactly what we want. Since Z is equal to the suction, then a graph of suction versus moisture content will give us the moisture content in the unsaturated zone. And that, of course, is the soil moisture characteristic curve. So here is a classic soil moisture characteristic curve. Now just a few differences here. Usually we plot this as the logarithm, but I haven't plotted it as the logarithm here. This is just matrix suction, not the log of matrix suction. And I plotted suction so that these values are becoming increasingly positive and large as suction increases. Now just remember that's equivalent, right, to saying if I wanted to plot the matrix potential psi, then it would be 0 down here. These would all be negative numbers, -1, -2, -3, -4, etc., right? So it's really very, very small difference here. But remember what we said. If we are at hydrostatic equilibrium, and if we define the water table as a datum, then the matrix suction is the same as Z. So I could, instead of matrix suction here, I could alternatively say this is just Z. And this then gives us the connection we want. So in other words, if we are 2 meters above the water table, right? This is 2 meters above the water table. Our matrix suction will have to be 2 meters, right? So that H equals Z minus the matrix suction, and that will be equal to 2 minus 2 equals 0. That's our condition of hydrostatic equilibrium, right? If we're 3 meters above the water table, then the matrix suction will have to be 3 meters, so that 3 minus 3 is 0. And if we want to know at either of those elevations what the corresponding moisture content is, we always use the soil moisture characteristic curve. So if we're at 2 meters above the water table, and the matrix suction is therefore 2 meters as well, to find out what moisture content we'd expect 2 meters above the water table, we simply read off the soil moisture characteristic curve. So at 2 meters of matrix suction, we get looks like here, we get a moisture content of about 0.15. And at 3 meters of matrix suction, which occurs 3 meters above the water table, we get a moisture content of, looks like about 0.06. So we can use this then to tell us the moisture content at any elevation above the water table. And in fact, this curve is exactly the moisture content of any point above the water table under conditions of hydrostatic, really important, under conditions of hydrostatic equilibrium. The soil moisture characteristic curve in terms of the matrix suction interpreted as elevation is the graph of moisture content above the water table, with Z now representing elevation above the water table. Now notice that this graph will be terminated at some point. So for example, in this point, in this drawing here, the water table was 3 meters beneath the surface, right? 3 meters beneath the surface. So the highest I can get above the water table is 3 meters, and I'm into the air, right? So 3 meters is the surface of the ground. So over here, I'm sorry, wrong graph. Over here, 3 meters then represents the surface, right? So 3 meters elevation here is the surface of the ground. And so the moisture content right at the surface can be found at 3 meters, and that once again we said was 0.06. And the rest of this curve below 3 meters would correspond to the moisture content in the soil from the surface down to the water table 3 meters beneath the surface. Now let's add a little twist here. Let's assume that we were at hydrostatic equilibrium and then it rained, and the rain filled in the pores in the upper part of the soil, so that our real moisture content graph, okay, looks like the one that has the blue line above and then it joins the red line below. So our real moisture content graph is going to be the one that sort of looks like goes like this. It goes down and then all the way around like that. Okay? Now, intuitively, what you should sort of think is, well, if I have this extra water in the upper part of the soil, that water is probably going to want to move down till we reestablish hydrostatic equilibrium, right? So your intuition should be that the water should be flowing down. But let's see if we can actually show how that happens by Darcy's law. Remember, Darcy's law is simply going to say that water is going to flow from high head to low head. So let's see if we can figure out what is the head at the surface. Surface located again 3 meters above the water table. So just to be clear again, the surface is here. This is the surface, 3 meters above the water table. Now at the surface, the moisture content is actually at saturation, which is 42% right here, right? So the moisture content at the surface is equal to 0.42. But we want to know the head at the surface, right? So what is that? Let's determine the head at, and I'll do it in terms of head at Z equals 3. Z, remember, is the water table elevation. So 3 meters above the water table, which is the surface. And let's do it at 2 meters above the surface, which is at the water table, which is a meter beneath the water table. Let's figure out what the head is. Now, in both of these cases, right, head is going to be equal to Z plus psi, or as we've been doing it, H equals Z minus the metric suction, which is the absolute value of psi, the positive value, right? So let's see if we can figure this out at the surface. So at the surface, at H at the surface, which is at Z equals 3 meters above the water table, we have Z, which is 3, plus psi. Well, what is psi? Well, the only way to get psi from a moisture content is to look at the soil moisture characteristic. So what we have to do is look at the moisture content at the surface, which is 0.42, and then using the soil moisture characteristic curve, the curve in red, convert that to a value of metric suction. So at 0.42 right here, that was the moisture content at the surface. According to the red curve, this sort of should make sense, the metric potential, which is the same in this case as the metric suction, when the pores are completely full of water, is 0. We're at the water table. It's the same thing as you would have found at the water table. So the metric suction at, I'm sorry, we wrote it, yeah, let's be good. We wrote it as psi or equals 3 minus the metric suction. Either way, this is equal to 0. Psi, or the absolute value of psi, is 0. So this is just equal to 3 minus 0, or 3. So the head right here, let's actually draw a picture of it. So here and over here now, we want to figure out, we've put some moisture into the soil. So here's our drawing on the left here, and this sort of dark gray represents now that I've added water to the soil here. So I've added extra water, it's a little darker gray. And I want to determine the head at the surface here, which is the head at an elevation of 3 meters, right, above the water table. And I also said I wanted to determine the head here at an elevation of 2 meters above the water table, right? Okay, so let's see what we got. So for the first one, whoops, I did this wrong again. So for the head, we ended up with a head at the elevation of, this is the surface here, right? We ended up with a head of 3 meters. So let's write that over here. So over here, we'll do it in, let's do it in green. So here the head is equal to 3 meters, right, at the surface. Okay, let's go back to the other points now. So let's now go to an elevation of 2 meters above the water table. So elevation, the head, we want to know the head at an elevation Z of 2 meters above the water table. So Z is 2 meters above the water table, and we have to figure out, well, actually we're going to use this one, right? So minus the suction at 2 meters. We have to read that off of our graph. So at 2 meters above the water table, first of all, let's find out what our moisture content is. So at 2 meters above the water table, according to our blue curve here, we have a moisture content of 0.28. So this is 0.28. And to know what the value of the matrix suction is, we have to go to our curve and say, oh, at 0.28 moisture content, what is the value of the suction at that value? So 0.28 is right over there. If we go to our red curve, then that corresponds to a matrix, let's see, 2, 4, 6, a matrix suction of 1.6 meters. So again, the way I get this is I take my moisture content and I follow the curve. I go to the curve and find the corresponding value of psi, or in this case, the matrix suction corresponding to that moisture content. The curve, the soil moisture characteristic, gives you the translation between moisture content and matrix suction. That's what it does. So I read off my moisture content, and then if I want to know what value of the matrix suction does that correspond to, I use my curve, and here I get 1.6 meters. So the head here at 2 meters above the water table will equal to minus 1.6, or 0.4 meters. So this is meters again. So let's go back and write that in here. So at 2 meters above the water table, we had a head equal of 0.4. And just to remember what we had at the water table, right, was the head of 0. So just as our intuition sort of suggested, right, what Darcy's law is going to tell us is a head is going to flow from high head to low head. It's going to flow from 3 meters down to 0.4 meters, right? And then further, it's going to flow from 4 meters down to 0 meters. So what Darcy's law tells us is exactly what our intuition sort of suggested should be happening, is that due to that extra water in the extra moisture in the soil, in the upper part of the soil, that is going to create a head gradient that will drive water downward through the soil until we once again, this will flow until we once again reestablish hydrostatic equilibrium, which is the soil moisture characteristic curve.